This is Welcome back to the channel. This is Structural and Stress Analysis by THG Megson, Arnold Publishers. So I've come to chapter 16, statically indeterminate beams. This is because I wanted to show this example of flexibility method. This is a flexibility method with two unknowns, two support unknowns. So this one we got to use simultaneous equations. So it says determine the support reactions in the three-span continuous beam ABCD shown in figure 16.17a. RA, RB, RC, RD, 6 kilonewton, 10 kilonewtons, C 12 kilonewtons per meter. And then, so there's three spans of 1 meter. It's symmetrical beam, apart from the pin obviously, but not a symmetrical load, so that makes it a bit more difficult. So the primary structure, that is remove. So so the beam is, so you got 1, 2, 3, 4, 5 reactions, but 3 equations of equilibrium. That means it's statically indeterminate by 2 degrees. That means, so if you take out support RB and RC, then you'll be able to use, it will be statically determinate, and then you've got to reapply the support reactions to return the deflection to 0 at B, so that's what diagram C is, and then apply the force at support position C, and take that back to 0, and that's diagram D. But what you notice as well is when you apply the load at B, the unit load at B, you've got to return that to 0 deflection. That's also going to move support C, so it's like a secondary deflection of C. So that means that the unit load at C will be a little bit less, because it's like that's where you need a simultaneous equation to solve it. So just quickly, you've got 6 kilonewtons, 10 kilonewtons, and 12 kilonewtons per meter for 1 meter. 0.5, 0.5, 0.5, 0.5, 1 meters. 6, 10, 12. So the total reactions will be 12 times 1 plus 10 plus 6. That's 16 plus 12. That's 28. 28 kilonewtons. So here we go. The solution is, it's clear from inspection that the degree of statical indeterminacy of the beam is 2. Therefore, if we choose the supports at B and C as the releases, the primary structure is that shown in figure 16.17b. We therefore require the vertical displacements VBO and VCO at the points B and C. Alright, I'll read that again. If we choose the supports at B and C as the releases, the primary structure is that shown in figure B, which is that one. We therefore require the vertical displacements VBO and VCO at the points B and C, because they've got to go back to 0, because in this beam, what we know is the vertical deflection at B will be 0 and the vertical deflection at O will be 0. So we release those supports, but then we have to return the deflection at those positions to 0, but it's got to be done simultaneously. Whereas when you remove one support, you've just got one equation. Now we've got 2 equations simultaneously. So the deflections may readily be found using any of the methods previously described in this chapter. So that's chapter 16. That is the unit load method, the moment area method, Macaulay's method, section 13.2. So the deflections are, that's for a unit load of 1 it's got downwards of 1. So I think he's using the unit load method. VB0 equals 8.88 divided by EI. That's the deflection. When you apply that 1 is when it's downwards, then the deflection at VB0 is 8.8 and VC0 is 9.8 over EI. We now require the flexibility coefficients A11, A12, A22 and A21. The coefficients A11 and A21 are found by placing... Oh, sorry. What I've done is this. I've done this wrong. Right. So hold on. If we choose the primary structure is that shown in 16.17b. Right. So the deflections in this beam, in this primary beam, the deflections at B and the deflections at C are, deflections at B, VBO is 8.88 EI based on that load condition. And the deflection at VC0 is 9.08 over EI in this beam. So these are the primary deflections. That's the deflections at point B and C, the primary structure deflections. We now require the flexibility coefficients A11, A12, A22 and A21. The coefficients A11 and A21 are found by placing a unit load at B, point 1, as shown in figure 16C. Then determining the displacements at B and C, point 2, because point 2 is then the secondary, I call it a secondary it's a secondary deflection, but it's the subsequential deflection at C from applying a point, let's call it the consequential deflection at point C from applying a load at point B. Similarly, the coefficients A22 and A12 are found by placing a unit load at C and calculating the deflection at C and then the consequent deflection at B. Again, any of these methods listed above may be used. However, from the reciprocal theorem section 15.4, A12 equals A21, and from symmetry A11 equals A22. Therefore, it is only necessary to calculate the displacements A11 and A21 from figure 16.7, 17C, because this is symmetrical, I guess, yeah. It's symmetrical, isn't it? It's a mirror. It's just saying a mirror. So A11 equals A22 because 0.45 EI. A21 equals A12 with 0.39 EI. The total displacements at the support points B and C are 0, so that VBO minus A11 R1 minus A12 R2 equals 0. VCO minus A21 R1 minus A22 R2 equals 0. Or, substituting the calculated values of VBO, A1, etc. in equations 1 and 2, and multiplying through by EI, so that's that one. VBO minus A1, 8.8 minus 0.45 R1 minus 0.39 R2 equals 0, 9.08 minus 0.39 R1 minus 0.45 R2 equals 0. Note that the negative signs in terms involving R1 and R2 in equations 1 and 2 are due to the fact that the unit loads were applied in the opposite direction to R1 and R2. Solving equations 3 and 4, we obtain R1 equals RB equals 8.7 kilonewtons. Then it's by solving these simultaneous equations. You're not showing how it's done, but you've got to solve these simultaneous equations because you move, say for example, 0.45 R1 plus 0.39 R2 equals 8.88, and 0.31 R1 plus 0.45 R2 equals 9.082. So you can eliminate R1, say R2 equals R1, and then put that in the first equation. The remaining reactions are determined considering the statistical so R1 equals RB equals 8.7, R2 equals RC equals 12.68. The remaining reactions are determined by considering the statistical equilibrium of the beam and are RA equals 1.97 kilonewtons, RB equals 4.65 kilonewtons. As I said before, the whole thing has to add up to 28. So you got 8.7 plus, let's say 9 plus 12.5. That's 21 plus, plus about 2 plus 4. So that's about right. In example 16.5 to 16.7, we have assumed that the beam supports are not subjected to a vertical displacement themselves. It is possible, as we have previously noted, that support may sink. So the right-hand side of the compatible equations A, 9 and 10, in example 16.5, equation 2 in example 16.6, and equations 1 and 2 in example 16.7 would not be 0, but equal to the actual displacement of the support. In such a situation, one of the leases should coincide with the displaced support. Right. So it is clear from example 16.7 that the number of simultaneous equations of the form of equations 1 and 2 requiring solution is equal to the degree of statical indeterminacy of the structure. For structures possessing a high degree of statical indeterminacy, the solution by hand of a large number of simultaneous equations is not practicable. The equation would then be expressed in matrix form and solved using a computer-based program. Thus, for a structure having a degree of statical indeterminacy equal to n, there will be n compatibility equations of the form V1 0 plus A11 R1 plus A12 R2 plus blah blah blah, blah A1 n Rn equals 0, Vn 0 plus An1 R1 plus An2 R2 plus da 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 plus Ann Rn equals 0. Or in matrix form, it's just as you can see there, V1 to Vn, A11, Ann, R1 to Rn. Note that here n is ns. The degree of statical indeterminacy, the subscript s has been omitted for convenience. Alternative methods of solution of continuous beams are the slope deflection method described in 16.6 and the iterative moment distribution method described in section 16.10. The latter method is capable of producing relatively rapid solutions for beams having several spans. Moment distribution method. Oh yeah. Okay, so guys, that was just a good example of flexibility method for two unknown supports in a continuous beam. If you've got any questions, please leave a comment in the comments. Thanks for watching. Please like the video. Please subscribe to the channel so I can make more videos. See you in the next video. Thanks.